All right. Okay. So so today I would like to tell you about a very recent work that I've done in collaboration with Mademoiselle on diffusion models. I find diffusion models very interesting. I think there is a lot to do, especially from statistical physics. So what I want to do today is to first give you an introduction. I will also go really in the detail of the math because it's very simple. This is also the beauty of it. And then I will tell you what we do. Now, what should I click to change? All right. Okay, so generative, I think generative AI is one of really the breakthrough that has been done in the last years. And clearly there are impressive results in image and text generation. And here I just, while I show you, I mean, diffusion models are the models, the method that are used in the state of the art for image generation. And now this, I mean, it's before they used GANs, but starting from 2020, actually, diffusion models are really the ones that are used. So here I just give you an example of images generated by diffusion models, which relate to what diffusion models are. And then, well, I'm sure that maybe many of you have played with DAL-E or its equivalent from Google. So here is, well, in which you do a diffusion model are used in the application for text to image. And here I create a 3D picture just yesterday for you using DAL-E, just to show you what they can do. All right, so what I want to do, so next is really explain to you what diffusion models are. And so diffusion models are something very simple. So let me introduce a little bit of notation. So you start with a set of images. Let's call it A mu. So it's just a vector in dimension n. Mu runs from 1 to p. So p will be the number of data. And what the models do is the following. So you start a Langevin equation. At time t equals 0, while the Langevin equation is initialized to the value which just corresponds to the image. And then you run a very simple Ornstein-Uhlenbeck Langevin equation. So one of the most simple Langevin equation. And I'm sorry, I know that there are mathematicians here. And well, this is dx dt. I know that it's not defined, but informally, let's say that there is no problem, as we do in physics. So you run this equation, and what you do when you run this equation is that you start from this initial condition, and this equation at long time will converge to independent, identically distributed Gaussian with mean 0 and variance 1 on each for each component of the vector. And so, well, visually, what you do is you start from a nice image, then you run this equation, and you transform this equation in white noise. You also know exactly what is the probability law of x at time t. Well, if you know what is the probability of the data, let's call it P0 of A. Well, it's very simple. This is just, you just integrate this equation, and what you find is that you just convolve this equation with the Gaussian. So you know what the probability P of t at a given time is, and what you see, what this Gaussian is doing, it's noising, actually. It's putting noise on the image. Now, what this diffusion model learn is they learn how to go backwards in time. So you see, you transform images, the probability distribution of images in white noise. Well, if you learn how to go back, so to transform white noise in an image, then if you want to generate a new image, it's easy. You just give a white noise, you just draw a white noise, you let it go backwards, and you get a new image. So it looks miraculous, but this is really what these models are doing. Now, well, to show you exactly a little bit how they do this, so the idea is the following. So how to go backward in time. So while in physics, we learn about time reversal. So this time reversal is a little bit different from what we do in physics, but is a generic property of stochastic equation, is that, well, if you know what is Pt of x, and we know what Pt of x is, well, if you take the log integral with respect to x, this is what is called score function. And now, if you use this score function and you define this Langevin equation, which is just a backward in time Langevin equation, this Langevin equation, what it does is really you integrate it, you just go backward, and it transforms white noise in the original distribution P0 of A. And this is an exact result. Now, the problem is that in general, you don't know the score function, but if you knew the score function, then this is allow you actually to go back in time and to transform white noise in the data. And this, well, so the idea then is that then you can use actually machine learning techniques to try to learn this score function. And if you learn it well enough, then you generate new data. And at least for me, which that I work a long time on stochastic dynamics and algebra equation, I mean, if you think about this, it just means that you start from white noise and you learn what are the forces that work on this kind of particle and transform a white noise. They make it move, these forces, and then this white noise becomes, I don't know, the face, it's the face of a man or the picture of a dog. Now, this idea, interesting actually, this idea of go backward in time and using this diffusion model came in 2015 in a paper by physicists, physicists at the boundary with machine learning, but still physicists. And if you see in actually the title of the paper, there was also equilibrium thermodynamics, and you will see I will discuss also some idea about topic equilibrium thermodynamics at the end. So, well, this was done in 2015 and somehow remained silent or until 2020, and then in 2020 really picked up a lot, I think, because people learned actually how to learn the score. So in this paper, I mean, they proposed the idea, but then starting from 2020, they learned how to learn, they understood how to learn this score from data, and then they started to be used everywhere. So, well, for a nice review, you can see this review by Jan, which is, I think, 2022, 2022. So let me tell you now how you learn the score. So the idea is the following. So, well, you have to learn this function. So these are the forces that you have to use. Well, this function is a function in high dimension. Well, if you have data, in principle, the idea is that you should, well, it's a regression problem in which you will parameterize with typically a deep net a function, and then this function should be as as much as possible equal to this function f. And so for the moment, let's define a population loss. So the idea is, again, well, for the moment, there are no data. So there is the exact PT of x, is the probability distribution at time t, is the denoised version of the data. And then what you have to do is that you construct a parameterization of this function in terms of parameter theta, and you want to minimize this loss function. And typically, they use some kinds of deep net, which has this kind of form. Now, you can work a little bit around this population loss, and what you do is you just develop the square. And so you have one term, which is s theta squared, then you have the cross product, and then you have f squared, but f squared has no parameter in it, so it's just a constant, we don't care. So if you look at these terms, well, this term here is the grad of log p divided by the grad of log p, so grad of log p means grad of p divided by p. So well, this p and this p goes away. So here what you get is the integral of the dx, st of x, and grad of p. So what is grad of p? Well, if you take pt of x, which is here, the grad with respect to x, will act on this Gaussian. So you just make an x minus a exponential minus t go down. Okay. So at the end, you end up with this kind of loss. This loss, which is the expectation over all the stochastic process, so over x and a, of s theta of x, and then x minus a exponential minus t divided by delta t. And now this is very easy actually to make it a problem of empirical minimization, because now once you have the data, so for each data, for each image, you run the Langevin dynamics. So you have one trajectory, you can also run multiple trajectories, but let's keep it simple. So for each image, you run one trajectory. So you have, and so what you have to do now is, well, for each data and each trajectory, well, you have just to minimize this empirical loss. So find the parameter theta of t that minimizes it. And if you find the parameter, then you find an approximation of the score. And then, well, you do it for a fixed number of times. So you discretize the Langevin dynamics in fixed within small steps. And then once you have it, then you can run your Langevin dynamics, and you can create images. So in principle, very simple. Of course, there is the parameterization here, and then there is also the fact of really how these things work. So what I want to do now, before telling you our result, is to tell you what is known from the theoretical point of view. And actually, what is interesting is very, very little this time. So actually, many physicists that work on this machine learning problem, the staff introduction say that it's a very important problem, but there is very little known, especially in deep nets. Well, there is little more, but I mean, there is a long tradition in math and computer science on this. And actually, on this case, there is actually very little known, meaning that even in math and computer science, there are not many work. And so the state of the art, let's say theoretical math results, have been obtained by a young researcher, De Bortoli, and also another one is called Doucet, who is in Oxford. And these are the kinds of results that they found. So very formally, what they tell you is that, well, if you find an approximation such that f bit of x is close enough to the score, to the true score, if the distribution of data is regular enough, then you can find different positive constants such that the probability distribution of the probability distribution that you get from the model is close enough to the distribution of the data. And close enough, so this is the total variation distance for the ones who know, otherwise it's just a distance. And you see that this is less than different factor. So big T is the time at which you run the Langevin dynamics, because, well, you cannot run it at infinite times. So you know that you start from the data, you run the Langevin dynamics, at a certain point you stop, and then you go backward in time. So this tells you that, well, you have to go long enough in time to have this term which is small enough. And then actually you see that when you run long enough in time, you may have a problem because it's go up. So you can actually keep this term if you take an approximation which is good enough, and if you take a time step in the Langevin equation which is small enough. So you could think that this is a very bad thing because it's exponential T, but actually if you do additional hypothesis on the data distribution, then this becomes a problem also. It's not as bad as it seems. Okay, so this is the kind of result that they have. And well, if you look at this result, there is clearly one or at least, or maybe two elephants in the room. So the first thing is, we all know that one big problem that makes the problem difficult is that the data are very high dimensional, which is what Mathieu discussed. And then there is the course of dimensionality, and then you should discuss how many parameters you need. And here, well, the dimension is not here. Actually, it's hidden in all these constants. So, well, there are many important questions that are open, and on which I think that physics can have to make progress. And so, well, let me tell you just a very small selection. Well, but the first I think the most important one is what is the role of the dimension of the data in all this business. And then if you try to understand this, clearly this is also related to with how many data, is what the role of the dimension of the data, and then how much data you need actually to have a good diffusion model. I will also try to tell you what does it mean. I mean, I can say what is a good diffusion model. It's not a question. It's a good diffusion model will produce an approximation of the probability distribution. These are probability distribution in high dimension, and well, what is a good approximation of the probability distribution in high dimension is not a trivial question. And then I think there is another question that I will not address at all, is what is the role of the approximation class? So well, they use what they call a UNet. They use some kind of deep net to approximate the score. And of course, one should ask, I mean, what is the role of the number of parameters that are used? What is the form? I mean, why the form and the vector is important, which are exactly the kind of questions that Mathieu addressed. But I mean, one should address also in this context. All right, so what I want to tell you in the following is what we did, which is the first attempt, first study of the role of dimension and also the number of data in the case of diffusion model. So, well, since there is nothing on the role of dimension, well, it's a lucky case in which we can start with the simplest model. So, what is the simplest model one can think of? Gaussian data. And okay, Gaussian data, of course, is simple, but here we take high-dimensional Gaussian data. So this will be the first example that we study. So high-dimensional Gaussian data, so what you do, I instantly divide dimension of the data, again, the same notation, P is the number of the data, and now we consider the limit in which the dimension is very large and the number of data is very large. And the vector of the data, so it's just a Gaussian vector, which has a certain mean zero and has certain covariance C0. And now C0 is an n by n matrix at n goes to infinity, so we should say something about its properties. And the property will be that the density of eigenvalue of C0 will converge to some function, to some well-defined function. All right, then let's apply the idea of the diffusion model. So again, I remind you, you take a certain number of data, then you run your Ulenbeck equation. Now in this case, well, since P0, so Pt of x is the distribution of x at time t, and well, what you have is that here is the convolution of the initial Gaussian with a Gaussian. So the convolution of the Gaussian with the Gaussian is a Gaussian. So it means that Pt of x is a Gaussian. So which means that the score, the exact score, well, this is the log of a Gaussian. So the log of a Gaussian is the quadratic function of x. You take the derivative, so you get that the score, the exact score is linear in x, which means that, well, has this form. So the exact score has this form, and you can compute it exactly, and the this matrix W at time t is just given by this expression. So you can see that when t is 0, this term goes away, and you get just C0 minus 1, so the inverse of, yes.
Just to understand, how do you define the dimension of the data? Not of this Gaussian data, but the real data.
The dimension, I mean, just naively, it's just the number, I mean, it's just for an image, I just define the number of pixels, and then maybe there is the color. You just, the most naive definition possible. And so when t is equal to 0, you see W is just the inverse of the covariance matrix of the data. And when t goes to infinity, this goes away. And when this goes away, you just get the identity times the temperature. So the system one is very simple, and the score is very simple at one time. All right, so this is the analysis in the exact case. But of course, I mean, it's not, we don't want to understand the exact case. We want to understand when we get a certain number of data, and we have a certain dimension of data. So what you should do, and please, well, ask questions if there's something which is not there, because I think I have less slides than to keep in 15 minutes. So yeah, good.
Sorry,
go ahead.
When you learn in practice, when they learn theta of t, do they learn different networks with completely different parameters for every time? Or
no, it's the same network.
So t enters as like a variable.
So the yes, t enters like a variable in the network. Yeah.
Just you add a column.
Yeah, actually, they don't even do it. They don't even do this time, this time, this time. They just throw at random the different times.
And so you have your input x and you add the t coordinate.
Yes, exactly.
Treated as your.
Yes. Well, sometimes, I mean, again, maybe this again, we have time. But here you see, here I define it at a given time. What they do, they define a loss function, which is over the whole trajectory, maybe with some weights depending. So they weight more the initial time than the long time, and then they just minimize it in one go. Okay, so in this case, Gaussian data, let's work out what they do in practice. So this, we know in this case, with lucky, we know what is the expression of the exact score. This in general, you don't know, with real images. In this case, we know, so we can say, okay, the score, I know that it's linear, so what I should do, I should use a linear score, and I should try to get from the data what is the matrix W that I have to use. So how would you do it? Well, you take this, you plug it in the empirical loss, and then you use exactly the form of the empirical loss that I told you. Well, you see, so this is linear in X. You just develop, you differentiate with respect to W, and at the end, in this case, you get an exact expression for the W, the empirical W that you get from the data. And the empirical W, well, you can express it in terms of matrices, which are nothing else than matrices that tells you covariance, empirical covariance of the process. So for example, this matrix T, well, this you sum over, so for each data, you have a trajectory. And so what you're doing here, you are summing over the T trajectory, xi mu T, xj mu T. So this is nothing else than the empirical covariance at time T of the Langevin process. And then M, well, it's similar, it's a memory matrix. So if you get D, you get M, well, you put it here, and this is your empirical estimation of W. Now, the question is, well, this is what you get empirically. This is actually in a lucky case because you know even what is the exact score, so there is no problem of approximation class. Now the question is, if you are in high dimension, how much data I need actually to get that this W is equal to this W, which is the exact one. And now you can see that you can start to, so the question that you can ask, what is the role of the dimension, how many data one needs to get a good diffusion model, and you can start to see how the dimension can play a role. And the reason is that imagine that you are in fixed dimension. If you're in fixed dimension, and this matrix T, if you want to estimate it in a good way, well, you just take P very large, and then since this, for different P's or different trajectory, are just independent random variable. So you just use the central limit theorem. This will converge. P will converge to the correct covariance. And if it converges to the correct covariance, then say click for M, and then you get back the true matrix W. Now the problem is that the dimension is large. This is a very large dimension. It is a very large matrix. And you know that, well, for a very large matrix, one has to be careful. So if you look at this is nothing else than a Wishart matrix for people that like random matrices. In the case of Wishart matrices, it's known that if the dimension of the matrix is of the same order of P, of the number of data over which you do the average, then, I mean, this empirical matrix is quite different from the true matrix. So you can start to feel that dimension will play a role, and there will be a competition between dimension and the number of data. So let's see. So at the end, in this case, it's nothing else than the random matrix theory problem to understand the competition between dimension and number of parameters. Yes?
The two matrices are not independent. M and D.
Yes, they are not independent. Yeah, they are related. Yeah.
That relation is relevant because for each of the two you can use several theorem.
Yeah.
The fact that the two are coming from the same trajectory plays some role.
Not for what I'm going to study. In general, the process in principle, yeah. But for what I'm going to tell, so the different regimes, no, it's not important. But you're right. I mean, if one want to study the backward, especially the backward diffusion, in principle, yes, there is a correlation. All right. So now, what is this random matrix theory problem? And I will just give you the key idea that allow you to understand what's going on. So let's focus again on this matrix. And so let me tell you exactly what I told you before. If I consider just the element ij, I just consider it ij, then when P is large enough, well, I know that at a certain point this will converge to the good value,Cijt, which is, let's say, the true covariance. And then if P is not infinite, there will be a fluctuation. What is the order of this fluctuation? Well, just of order 1 over square root of P, just use the central limit theorem. Now, what I can do, I can rescale actually this 1 over square root of P. I will rescale it in this way. I will say we write it by square root of P in the denominator, I put the square root of N in the numerator. And so it means that this fluctuation I write it by square root of N divided by P times an element, Rij, which is a order 1 over square root of N. I hope it's clear. I just put this one square root of N on top, and so there is a square root of N on the bottom. Now, the interesting thing is that if I write this way, now the matrix dt is Ct, the matrix that I'm interested in, that I would like to have as an estimation. And then I have an error, and this error is square root of N divided by P times the matrix R. Now, the matrix R has the correct scaling in large dimension in such a way that the density of eigenvalues is of order 1. So if you, for example, if you think about the Gaussian orthogonal ensemble of random matrices, to get the semicircle law of Wigner with eigenvalues of order 1, you must have eigenvalues, the elements R, which are 1 square root of N. So if I write it this way now, well, this is a problem that has been studied a lot in recent years for simple matrices. So if you take a deterministic matrix C of T, and this R is a Gaussian, is a matrix for the Gaussian orthogonal ensemble, which is not the case in our case, but if it were, then this is called the Roden-by-Porter random matrix model, and there have been a lot of works, this from physics and then from math, that tell you that, well, if P is much larger than N, the density of eigenvalues of D is exactly the same of the density of eigenvalues of T when T and N go to infinity. But the eigenvectors are completely different in principle. If P is much larger than N squared, so if you have much more data than dimension, so it's P is larger than dimension squared, then really you have a convergence between D and C, meaning that the eigenvalues of C are the same as the eigenvalue of D. up to subleading terms, and the eigenvector are also oriented exactly in a good way. Okay, so this is what happens for the deterministic matrix plus GOE. In our case, if you see what CE, I mean, we are in a different case because this is a more efficient matrix, and this is a bit more complicated, but that's the idea. So what we have, that the matrix that we want to estimate is corrupted by a random matrix times something which is square root of n divided by p. And we can use the same kind of argument that we use for the Rosenzweig portal model. So cutting a long story short, so what you get in this case is that you find now in the generative diffusion for Gaussian high dimension, you can find three regimes. So what the diffusion model does is that it's going to generate Gaussian data. This is clear because we start from Gaussian data. Then the Langevin equation gives you a Gaussian trajectory. Then you go back again with a Gaussian trajectory. And so it's with the Gaussian. And so with the Gaussian, it means zero and a certain covariance. And the question is how these covariance resemble the true covariance of that you have at t equals 0. And so what you find is that if the number of data is much less than dimension, then I mean the model is clearly wrong. This covariance matrix has nothing to do with the true covariance matrix, just I mean the diffusion model is just producing nonsense. Now there is a second regime, which is the number of data is much larger than the dimension, but C is less than a dimension square. Then you get the same density of eigenvalues of this matrix, that's 0, but different eigenvectors. So what this means is that if you look at the generative process, if you look at quantities like this, x of x divided by n, so this quantity, which is nothing else than the trace, is related to the trace of C, which is related to the integral of the spectral of the density of eigenvalues time lambda. So this would be correctly reproduced. To a certain extent, the global strength of fluctuation will be correctly reproduced. But if you want to actually know what is the direction in which you have the fluctuation, so the eigenvector, then it will be wrong. And also the interesting thing, which is more, I think, for mathematicians, but it was suggested to us from his anonymous referee, is that so you can look at the distance between a high probability distribution dimension, and this distance has been discussed a lot in recent years, especially in connection with optimal transport. And then, well, you know what it is, the 2 versus time distance. In this case, you find in this regime the 2 versus time distance between this high-dimensional Gaussian and the high-dimensional Gaussian, which corresponds to 2 process, vanish, whereas different from 0 here. Now, let's look at the third regime. The third regime, in which the number of parameters is very large, it's larger than the dimension square. In this case, really the generative process is good. Eigenvector eigenvalues are good, so everything, the direction of fluctuations is correct. And in this case, what you get is that not only the 2 versus the distance is 0, but also the total variation distance, which is a very restricted, I mean, it's very requiring distance for probability distribution in high dimension. Also, this one vanishes. So I think what is interesting here is that, of course, it's a very simple model, but you start to see first how the dimension play a role and how this is in competition with the number of data. And you can also see that actually when you say that the generative models is good, well, it depends what are you looking for. So if you are looking to this kind of variable, then it's good. But if you're looking really to the direction of the equation, so this regime is bad, then you have to clean this regime. Yes. Well, yeah.
And the time doesn't play any role because I stopped before forgetting completely the initial condition and that.
Yes. So in this case, we didn't look at the time, but this is just what I'm going to do in the next slide. But you're right. Here in this case, we just went to infinite time or very large, and we came back later. But that's an important issue, but I think it's even more interesting on what we're going to follow. Yes.
Already to say, even if the eigenvectors are wrong, still if you are looking at any direction and looking at the variance in different direction, you already have it in the second regime.
So to take a direction, yes, a direction at random, yes, yeah.
Yes, so you have a good variance in all directions.
I mean, it's, yeah, if you take a random direction, it's more or less orthogonal to all the eigenvectors. So I mean, it's tricky. I mean, you fix the direction. If you fix the direction and you take it at random, then it will be good. I agree. But if you want to know what are the important directional fluctuations, then you won't know that.
Well, even if you take the eigenvectors, you have a matrix that is approximation. Even if you take one eigenvector of one and you bracket it on the other, you get a good eigenvector.
No, I can get a good eigen. I don't think so. I mean, it's one eigenvector is really completely decomposed on all the other ones. It's just because, well, yeah, I mean, they're very sensitive to perturbation, the eigenvectors, so they just hybridize completely. All right, so let's now, so this is a simple case, Gaussian high dimension. So, but we wanted to go a little bit beyond this, and so we want to add a distribution of data which is less trivial. And in order to do this, well, we are statistical physicists, what kind of probability distribution high dimension we can have that are non-trivial are the ones that come from, let's say, phase transition. I mean, the one that you study in statistical physics, and especially at low temperature where you have a phase transition. So, well, you can have many things in mind. So, I mean, it's ideal models, I mean, crystal, liquids. So, for the moment, let's say any standard statistical physics distribution in the when the system size is large, it's nothing else than the probability distribution high dimension. And we want to be in the low temperature case in which the symmetry is broken. So what this means is that in principle, while we give to the diffusion model, we give different configuration. Some, let's say, that think that we are considering the ferromagnetic system. So some will be positively magnetized, some will be negatively magnetized. We transform everything in white noise. And then the system should be able actually, well, to generate some configuration which are positive and some configuration which are negative. And of course, in our head, there was also the idea that the different phase in the circumstance maybe one could think of them as different classes. And if I had a dog and a cat, and then well, I transform in white noise, and then the system has to be able to give a cat and dog back. And so just to give you, I mean, this is a very simple one-dimensional example in which, well, you have two Gaussian here, you apply the diffusion, you transform it just in one Gaussian, and the system has to be able again to go back and break the symmetry. So this is the trajectory of what the diffusion model does. And what we ask is how the system is doing this, but now in very high dimension. Okay, so again, we in the traditional statistical physics, what we can do is, in first thing, we can look at the simplest model ever, and the simplest model is of phase transition is the Curie-Weiss models, in which we take Ising A, which are plus or minus one, and we are full, and I mean, everyone interacts with everyone else within interaction of one array. And if beta is small enough, there's a phase transition with two positive, I mean, one positive, one negative states with magnetization and stuff. And now the thing that we do, we want to play with, we put a magnetic field which is very small. So here is the order 1%. Because what we want to have is that we want to have the weight of the two states, the plus and minus, is not 1/2 and 1/2, as we have in the usual symmetry breaking case, but it's going to be, I don't know, 1/3 and 2/3. Because what we want to see is that what we also have in mind is, imagine that I train the system, when I train a diffusion model, when I train, there are some, I don't know, some more images of one class than more images of the other class. Is the actual diffusion model is it able actually to get this kind of information right? So the weight, the statistical weight of the different classes. Because somehow, I mean, our intuition was that maybe you get it right, and you always see cats and dogs, but maybe actually the weights of which you get cats and dogs maybe is wrong, or maybe it's more difficult to get. And we are going to see that this will be the case. So, and then the other thing that we want to ask is, so this is why we take this h value by n is the dimension always. And so the other thing we want to know is, in this case, it's exactly solvable. Let's see how actually the diffusion model, like in this case, is going to generate this symmetry break. Okay, so in this case, oops, it's simple enough to be completely solved. So in this case, we don't play the same game than before, in the sense that we don't work for the moment with a fixed number of data. So we just look at what is the exact score. So how actually a diffusion model that works perfectly, how it works. So in this case, we can compute the score exactly. So I don't give you an expression of the score, But I just tell you what I mean. That's true. What happens at the beginning of the backward process? You start with white noise, and you start to run backward the diffusion process. What kind of non-German equation we have, and how it's able actually to reconstruct the images? So, well, first at the beginning of the backward process, sum over I of xi, well, xi are just IID variables. So this sum is order square root of n. So if you divide it by square root of n, you get a variable which is order 1. And on this variable, you can actually write what is the evolution of this variable. So here is simple enough. Also, mu verify non-German backward non-German equation. And here you can compute exactly the V on the potential. And the potential is, well, there is clearly x of two different kinds, depending whether square root of n exponential minus t, so square root of dimension times exponential minus t. So t is very large at the beginning of the backward process and is very small at the end of the backward process because we're doing time reversal. So what you see is that at the very beginning of the backward process, here what you get is that V is an inverted potential like this. And now, since there is an H, it's not around 0, but it's actually an inverted parabola centered somehow to the right in this case. So what happens now is that when you start the process, so mu will be somewhere here, then because of theta will start to diffuse. But what if it's, let's say, from this side, typically we go down, so we increase in this direction. If it's on this side, we increase in this direction. And since the parabola is slightly shifted to the right in this case, because H is positive, so we will have more trajectory that will go to the left than trajectory that will go to the right. So this is how the systems start to have different weights. And now when the square root of n exponential minus t is much larger than 1, this is the potential that you get. First thing that you can see is that H is not there anymore. So there is no more any information in the backward diffusion process about the weights. And here what happens is that here the network and the symmetry, there are some trajectories that are going down this way, some which are going down this way. The barrier here has become very, very large because what is the orders for the exponential minus t, so it's never going to go back. So the symmetry has been broken, and really the parameter at which you have the symmetry breaking is exponential minus t square root of dimension. So, well, so here we see really how the system breaks the symmetry, and we can also show that with this kind of algebra equation, with this potential, since we have the exact score, so the system reconstructs exactly the weights. But what is important is to see that reconstructing a good way the weights, you have to be very, the model has to work very well at the very beginning of the backward process. So this is when everything is decided in terms of the symmetry breaking and the weights of the different classes in the generative process. So this is what happened in the revised model. Can one be more general than this? And the answer is yes. So actually you can do this, you can get this result in any kind of statistical physics model. So you don't need to have new field, you can take a model in 3D, you can take particle models. And the next thing is, and the way to do it is the following. So here is the way in which I write the backward process. It's just this inverted non-German equation. Here is the score. Now the very interesting thing about the score, and this is also why I think all this is related to how equilibrium thermodynamics and also all this idea which came from Joyce, is that, well, the score, if you look at what it is, and it's a simple, but there's a simple part which does xi. And then what you have here is this is the derivative of the free energy with respect to an external magnetic field. So this is the free energy of E of A. So if you know the distribution at the beginning, then you compute the free energy, and you compute the free energy as a function of the external magnetic field. If you know this free energy, then you know the score. And what you have to do, you take the derivative of the free energy, and you evaluate with an external magnetic field, which is just equal to x exponential minus t divided by the vector. The fact, of course, is that in general you don't know the free energy as a function of the so that the problem that if you knew it, then you need to know what is the Langevin equation, you know the forces that allow you to go backward and back. Now, why this is helpful is because now if we study a case in which we have symmetry breaking and we have weights which are slightly different between one phase and the other, and we are at the very beginning of the backward process. So the external magnetic field is very small, you see, because there is this exponential minus t, and t is very large. So we can actually write the exponential minus t direct, like a sum over the different pure states that you have. And then, well, the external magnetic field is very small, it's slightly breaking the symmetry. So you have a sum over I of Ci, and this is well, the magnetization is I alpha, is the magnetization of the pure front I of the pure state alpha. And this is actually something which is completely general, and you can always do it if the external magnetic field is small enough, which is the case at the beginning of the network process. Now, using this expression, you just plug it in here, and you have a general expression of the score at the very beginning of the backward process. And again, you find something which is a generalization that I told you before. This is going to be a sum over alpha of the weights that you want to reconstruct. Exponential of nu alpha x. Nu alpha x is the projection of the vector x over the direction of the magnetization that you have in pure state alpha. And then you have this factor, which is square root of n over exponential minus t. So, but just cutting the long story short, is similar to what we had before. So you will see that the weight matter, and you really reconstruct the weight that when square root of n exponential minus t is more, or it's order 1. And when this factor becomes very large, well, then the symmetry is broken, and the system is committed, and you have lost any information about the weights. So in this example, if you think about it, this is a very low-dimensional example, in which you have just one dimension, but what it means is that at the very beginning, the system will have this phase transition, the path, so the system will commit, some trajectory will go this way, another will go this way, and once this region, which corresponds to square root of n exponential minus t, is passed, then that's it, the system is committed, we never go back, it will go on this way or on this way. So this clearly tells us that, as Federico was asking, is it's very important when you stop actually the Langevin equation in the forward process. If you stop it too, not far enough, you are in trouble. If you stop it here, well, probably it's going to be very bad for the generation process. And what is the time in which this depends on the dimension of the data. So, well, the answer question is what about images? That's all this work for images. So, for images, we don't know what is the probability distribution of A, but one can do experiments. And so, actually, there has been done some experiments by the Biroli at TNS. So, what he did is, well, I think he took the CFAR10, and let's say he considered two classes of CFAR10. So, in principle, each class is represented with 110 and 110 and 110, because there are 10 classes. But you can construct an artificial data set in which, I mean, one class is there, I don't know, a little bit more than the other class. And then you try to see whether the diffusion model is able to first to get back correctly the images, and second to get correctly the weight that you have put. And the answer is, well, he really saw exactly what, I mean, without doing any analysis in terms of dimension, but he clearly saw that the system is able actually to reconstruct images which are not bad, but to get the weight correctly, you have to go to runtime and to be extremely precise in the estimation of the score a very long time. Then there is another numerical evidence which comes from a paper which is very recent, which is June 2023. So here what they do, you cannot see, but it's not important. So this is what they do is that they do exactly what I tell you. So they run the Langevin process until a certain time, and then they go back. And this is a value which is so is low if actually the system is working well, and it's high if it's not working well. So it's something, it's a metric that is used to see how much the probability distribution of the generator is similar to the probability distribution of the inputs. And here what you have, that maybe you cannot see, on the x-axis is the time at which they stop. So here is a very long time, here is a very short time. And here is also what, so you see what they say is that there is a certain time at which clearly, if you go below this time, then this system is going to be very bad. If you stop it too early, and then there is another, if you go beyond this time, then it's actually going to be good. And here is an example. So here is when you stop, is the quality of the image when you stop it too early, is the quality of the image when you stop it very early. Okay, in the indirect evidence, it's not a direct evidence, but it's an evidence that there is a specific time scale at which things really change. And then what they did also, because they were also triggered by the idea of symmetry breaking, is that they compute, so here you have two classes, and they compute actually the potential, which in the direction, which is a linear interpolation between one image and the other. So they are not, I mean, it's the potential that you have in principle in the backward process, in principle, it's a function of many, many variables, but you can always look at this function just in one direction. And so what they claim here is that this time scale that they find here is the time scale over which this potential go from, let's say, 2 wells to one well. So in this case, remember what I showed you before was the potential which was inverted here. Okay, maybe. Yeah. Yes.
So only for one database, I think that a very large time is worse.
If you go to very large time, it's good.
No, yes, but one of the figures, the one on the right.
This one?
Yeah, on the left. On the left.
Ah, this one. Yeah.
Yes. Up, right.
Yeah.
This is going down.
Yes.
So do you know something? Is it atypical or?
That is going down if you go to very
Yeah.
No,
When you reach
not
a
really. Yeah.
good level, you see.
Yes.
And then for all the other database, you stable level, while there you go down.
Yes. So I don't know. I don't know if this is related to some kind of overfitting. So in reality, I don't know. I don't know. So I know that there are problems related to the. Okay, let me see. So this in this case, when it goes up, it means that. Okay, that's good. No, I think it's probably this is. So this is when you stop at very early time because it's the inverted time. So here is downtime. Here is. So here the fact that it goes down is probably just an error bar.
Sorry.
I'm sorry, it's the way the cloud will be. So, and so they claim that actually this will be the potential that I showed you before, but it's inverted, and also in that case, their case just in one dimension, so it's much more complicated things. But they claim to observe this kind of symmetry breaking that I told you. In reality, I'm not sure that it's what you can do if you numerically, but I'm not sure that it's exactly at the same time that they have here, but it's some evidence that they have. Okay. All right, so now I can conclude. So what I wanted to do today is to present the first study of high-dimensional diffusion model. And the two messages maybe is one is that clearly we see that there is two different time regimes. There is the time regime related to, I think, symmetry breaking, and probably in images, the formation of different classes. And here it's important if you want to get the weights right. So getting the weight of the different classes would be, for example, very important for all the discussion about fairness in machine learning. And then actually once the system has committed, one has committed, and then it will just each one on its class or on each phase if you have a statistical physics model. So we were able to study the simplest case, which is high-dimensional Gaussian, the competition between number of data and dimension. And they also discussed what does it mean that the diffusion model is good. Well, we have seen that, well, it depends what you ask. So there are some things, some regime in which a diffusion model can be considered to be good if you look at some observables. But then if you want to be extremely precise, then you have to have a very large number of data. Now there are, I would say, well, I just do three perspectives, which are three things which we are working on, but I think there are many, many more. So the first thing is, in all my talk, I always knew what was the exact score. And in the Gaussian case, I then use a numerical minimization to get an approximation of the exact score. But then in images, you don't know what is the exact score. So there is clearly a discussion about what happens if you use, well, an approximation for this exact score, which maybe is not good enough. And why actually the approximation that has been used with this kind of architecture, which I showed you, the kind of deep net, which goes down then goes up again, why it's good. So there is a discussion to do and things to think about. What are the good approximation classes? What are the good architecture? And why they are good given the data that we have? So what Mathieu discussed before. So then I think there is, in this context. So it would be nice actually to discuss the competition between the number of data and dimension. So in cases which are more difficult than just the Gaussian. And the easiest case would be to repeat what we did for Gaussian for simple multidimensional distribution like Curie-Weiss. So in the case of the Curie-Weiss case, I just discussed the exact score, but of course I can play the same game in the Gaussian case. So I can take an empirical, I can take empirical minimization that fix the parameter and see how much data I need, given that I'm in large dimension, in order that the diffusion model works well for the Curie-Weiss. One can go a little bit beyond and to models which are better for statisticians, like Mr. Gaussian. And then actually, then one can go also towards realistic application. So for and problems actually, well, there is realistic application, for example, is in painting, which is in the case in which you just know a part of the image, and then you want that your diffusion model actually create an image which fits well with just this small piece. And it's something that I think it can be discussed and has very nice relationship with things which are point to set in with the physics. And then there is the copyright problem, quote-unquote copyright problem that Carlo discussed. So here clearly there is for application, if you talk to people from DeepMind, what they really don't want is that your diffusion model recreate an image that has been used for training. Because then they have huge problem on copyright. And it's true that if you think about it, the only things that you know is the distribution of data, but it could be that the original distribution is just delta function exactly localized on the data. So if your model was perfect, you should be able to reconstruct that. So it would reconstruct the data from which it started from. But it doesn't do. Well, actually, in some cases it does. And so understanding when it's going to do it or when it's not going to do it, I think it's a very interesting very interesting scientific problem on which people are really very, very interested. All right, and this side maybe
When you do the forward process, so you take the data and you add the nodes. Can you interpret the P of X that you get as the effective model with a higher temper? So it's like adding temper to a model. And so the next question is, when you say that the time is not enough to achieve the perfect performance, because you are still below the critical temper, so you then go up to the parametric phase, so you can recover the whole distribution correctly.
No, I don't think it can be actually thought as temporal, because in a sense, only when you are at times in which scale like log n, the system is always in the symmetry broken phase. So you are putting noise on top of it, but you're not putting the noise as you would do it creating the temporal. I think it's a different kind of noise. I think there might be actually an interpretation with cost grading more than temporal. So if you add noise, but which depends on scale, then adding the noise would be more like a cost grading. So in this case, you just look in noise which doesn't depend on scale, so it's less interesting. But I would think it's more like a cost grading than a change in temperature.
In any case, the critical time that you need in order to make it, does it correspond to when, for example, you have a chronicity? So your simple two Gaussian problems.
Yes.
From a distribution where the two Gaussian
Yes.
At a certain time you get a chronicity.
Yes.
So can we relate the optimal time to sort of the chronicity in the induced distribution?
Yes. So the high-dimensional distribution has a phase transition at the time which goes like log n. But then, maybe you can interpret as temporal, but I don't think it's a problem. Yeah.
Two questions. What's the relationship between painting and self-supervised learning?
In painting and self-supervised learning? Well, because what you do here is that you learn a diffusion model on images, and then what you want to do is that you want to have a method that you should probably say, okay, diffusion model, I give you just a small piece of image, you should generate new image which match well with this small piece. But you don't want to reconstruct the image which has this piece inside. So again, you don't want to reproduce the training set. So you just want to reproduce a new generative model if you want, but that produce images that match well with this part.
One question. So you told us about the time scale that depends on the dimension of the data. But now if you have a finite training set, you may also have a time scale that has to do with when is it that data points start to meet. The diffusion is enough to bring them together.
Yes. So
yes. Example you give, do you think it's more one or the other, or I mean, you get some empirical example as well.
Yeah. So I think it's the time in which you have a blurred. So I think it's this time scale is more related to the copyright problem in the sense that there is a time at which you realize that your distribution is just makes an average over this, and this typically is extremely small time. So they're really different.
Thanks again for the talk. Besides the mathematics, can you give us some intuition on why the first stages of the backward forth process are so crucial to guess the right probability distribution? Because when you measure the score, I get the feeling that if you measure for long enough, at the end of the process, which is the beginning of backwards, is just asymptotics, Gaussian going to Gaussian. How does it contain so much information that when you go backwards, if you miss that, you are incomplete?
I think the reason is that if you think in terms of the data has, so let's think about Gaussian process, which is easier. So they have a Gaussian process has some direction in which you have very strong fluctuation. And this direction, so if you add noise, these are the ones that will disappear at last. So I think it's also what you see when you see the images, you start to see the form of the image as the first thing, and then there are all the details that arrive. So I think it's one thing which is a very big feature that has some face as a very strong component of the signal, and this is the one that disappears last, and so it's the one that in the backward it will recreate first.
So this is also something to do with the fact that you mentioned, I think at the beginning, that when you learn the score in the net, you put more weight on the last or the first one.
No, actually, what they do, they don't think about this. So what they do is they put okay. So they play with the weight at the beginning, and they not at the end, and they play with the weights at the beginning. And the reason is that they don't want to have this copyright problem. They don't want the system collapse back to the original data. So this is why they do so. And instead, at the end, they don't do anything.
In principle, one might be interested in guessing very well at the end of the process instead of the beginning.
Exactly. Yes. But then, for example, they don't ask. So I think if there was no paper that asked the question, so typically you see the system is good because, well, the images are good, and they don't think, for example, to get the weights right. So having the idea that they get the weights right, then you want to put a lot of precision at the beginning.
Thanks.